our focus in particular, my focus in particular, and that of my group, is on how do we help people that are at the front lines, that have to make decisions very rapidly, they're in tactical situations where they may not necessarily have the luxury of evaluating huge volumes of data at some leisurely pace to come up with decisions. These people have to get information very quickly and make good decisions based on that information. So this is the team. My name is Ed Morris, and this is the team. Dr. Jaime Carbonell is in charge of the Language Technology Institute here at CMU, and he just recently won a major international prize, so it's great to work with him. Ben Bradshaw, Aubrey, and Kevin work on my team, and Peter and Dagun are graduate students. So that's kind of the way we assemble our teams a lot at the SEI. It's SEI people, campus people, leading researchers, and that's kind of our goal. So, some of our previous work, we developed a platform to do real-time analytics of streaming data. It was initially focused on Twitter, but it can do other forms of text at this point. And then we deployed it. We deployed it at public safety situations, at the Little League World Series, the visit of Pope Francis, and several major concerts that were held outdoors. We also did some retrospective analysis of Cairo and Benghazi that we can talk about in terms of the tweets that were coming out of those two events surrounding the death of our ambassador and 3 other Americans in Benghazi. But we found some things out. First, it's not easy to recognize events. Most of these event recognition capabilities, what they really do is they're searching for keywords. So you tend to get lots and lots of false positives and false negatives. And it's not a very good solution at this point. The second thing we found out is that it's hard to determine how credible the information you're finding in social media is. In this particular case, we were focused on social media. For example, when we were working at a Little League World Series, there was a bomb scare that kept going around and around and around in social media. Well, it turned out to be a hoax, but that's a hard thing to figure out in real time. So the question is, how credible is the information you're finding out? Third, is there a pattern of events that you could somehow extract from this massive data that could be coming in from multiple sources? And finally, can you predict things that may happen based on what you know, or that have already happened based on the pieces you've seen? So, what we're focused on are what are called patterns of life or scripts. Now, patterns of life is typically the term that the DoD or many organizations use to represent kind of stereotypical sequences of events and interrelationships among events. The research community calls these things scripts. And what we found out from talking with analysts is analysts have a huge problem right now, but DoD analysts in particular, but I'm guessing across other organizations as well, and that is that many of the people that are doing analysis look like me. 60 years old, approaching retirement, and all of this, it doesn't look like any of you, by the way, just like me. So many of the analysts are at the verge of retirement, but they have all this incredible knowledge in their head about patterns they've seen before. It turns out that the young analysts who are coming up don't have that experience to draw on, so they don't recognize these patterns quickly. We were asked whether we could find a way to help young analysts get better at it, to be able to recognize the patterns more quickly. So let me give you some examples of what we call patterns of life or scripts. On the left is a picture of ISIS, an ISIS group, and when Haji Balair, I believe is how you pronounce it, was taken down around 2013, he was found with notebooks and notebooks and notebooks of ISIS scripts or patterns of life. This one happens to represent what they did when they went into a new village or community to take it over. Very common pattern they were using. There are other examples too. The situation with Russia and the Crimea. There actually were social media posts of people moving the missile launcher from Russian border into Crimea, where it was launched and took down a Malaysian airliner. Other situations as well. There was lots of information out there about buildup of Russian military capability in the area bordering Crimea prior to that situation that developed. And also, there are many other situations as well. But these things happen, and they're scripted. We do them themselves in our military. We ask our military to train to do things in certain ways. If we can begin to recognize those patterns, then we can understand much more quickly what's going on. So, our long-term goal. Oh, by the way, I apologize for the word salad up here. When I looked at the slide this morning, I said, oh, I probably set the wrong version of the slide. But I think you can get the basic meaning. And that is what we want to do is recognize event, validate those events, recognizing patterns across events within textual information, and then move toward interpolating to understand previous events and extrapolating for the future. So our objective for FY16 is try to understand what the challenges of script learning are. And we ran into some. No surprise. First of all, as I already kind of hinted, the event recognition capability is pretty primitive in many cases. Some of the best work is being done here at CMU, but what we found out is that if there's an event that's totally contained within a sentence, a single sentence, we do a pretty good job of parsing that sentence and extracting the event. If the event crosses multiple sentences, it's a little more questionable, and there's work here being done at CMU to improve that. But the real key is events that cross multiple documents. So you have some piece of information in an analyst report, some piece of information in some social media feed you perhaps got, something in a news report. You want to combine all those pieces of information. It's a very difficult challenge. Another problem is establishing relationships among those events. Credibility analysis, I'm not going to talk about here, but we have a poster outside that talks about that if you want to see how far we've gotten on that piece of the work. And finally, how do we create scripts on the fly? Remember, we're not assuming that we have the scripts pre-developed. We may have some pre-developed, but we want to be able to build them on the fly as the data comes in. Okay, our approach. First of all, I wanted to talk very briefly about events. Actors, activities, time, location, and you can imagine many, many other fields involved there. But just a very simplistic approach we initially took. We had a problem, as I mentioned, extracting events. We tried to use the state-of-the-art in event extraction. It wasn't very good. So what we did is we went to something we understand a little bit better, which is baseball. And what baseball has are box scores, huge volumes of data that are very, very good about capturing events in the baseball game. So that's what we used. We were focused on extracting the scripts in real time, or not in real time, I shouldn't say that. We were extracting the scripts from streaming data. We weren't necessarily focused on performance and volume at this point. And we found out as we went along, we had to learn the constraints of baseball. We had to learn those from the data coming in. Well, how many outs are there? Or can this play follow that play? That kind of stuff had to be learned. So, and then based on this, we generated the script that represents all of that data streaming in as individual events of a variety of baseball games. This is how we did it. It's a pretty simple algorithm. I would almost argue it's what Bill talked about. Bill's gone. Oh, there he is. As kind of the old-fashioned AI. Okay? Although we're moving more and more toward some of the newfangled AI where we do far more learning than the very simplistic stuff we did initially. But the algorithm is actually pretty simple. We read in 500 events, and we learned the constraints based on those events. We learned two particular sorts of constraints. We could have learned more, but those are the ones we focused on. Then, as we got a new set of sequence of events coming in, we said, do these match the script within some reasonable approximation of match, or if not? Okay, if they did match, they became candidates for insertion into the script. If they were totally unrelated, they were kind of put aside. Okay? Then, at the end, we said, okay, well, if these things match, or they appear to match the script, are they consistent with the constraints we learned? If they were, we inserted them. If they weren't, they still stayed aside. And then we kind of had a timer. After so many events, you want to get rid of all of those things that were not consistent with anything else. It's kind of a singleton in your data, and those build up over time and don't serve a useful purpose. So here's an example of how, let me just check my time here. I'm good. Okay, here's an example of what we did to match a script X and a sequence Z. We looked for 3 types of changes between the data coming in and the existing script. One are their transpositions within a block. So the A on the far right over there occurs after the B versus the previous case where it occurred prior to the B. So that was a transposition. Another thing we look for are exact matches. If you have an exact match, all is good, obviously. But we're also looking for deletions. Then we had a very simple similarity metric. If you traversed all the pathways in the developing graph and determined how close a match you had, if you have a close match, then there's at least a likelihood that it's a candidate for that existing script. So that was our similarity measure. How do we prevent invalid pathways? And this is what I was talking about where we needed some constraints. Well, so here's 2 examples of an invalid pathway in a baseball game. You have, if you look on the far left, B, whatever B is, follows B. So it could be 2 out 2s. Can you get 2 out 2s in a baseball game? Not typically. There may be some weird situation where you can, but I'm not aware of it. Or so in this script on the far left, event E follows event D. Does that have to be the case, or can you reverse the order? Can event D follow event E? There are a variety of ways to learn constraints. You can go to the expert analyst, okay, and the expert analyst probably from a baseball game could tell you what the rules are. And effectively, that's what you capture from experienced people, that script, right? You can learn it, and this is something we're going to pursue next year, from a curated report. So if you think about an analyst report, which is carefully crafted, identifies people in a consistent way, probably identifies events in a consistent way, can you use that to train to understand less curated data? That's something we're going to try next year. The other way to do it is what we did, which is learn it directly from the data, the constraints. You can do it at the same time, so you're learning you're learning the constraints at the same time you're learning the scripts. That's pretty hard to do, and it requires a lot of memory and a lot of time. We didn't go that route. We just took the first 500 half innings, and we learned the constraints of baseball, 2 very simple ones based on that. So that's our approach. You could also learn it from labeled data. We did not do that initially, although we had a kind of simplistic way of learning it from labeled data, if you think about it. But if you had a lot of labeled data, then you could learn those constraints with there are many machine learning algorithms that could apply. So when we updated the script, we were always checking against the constraints to see if it was a legitimate script in baseball. Here are the 2 constraints we focused on. First, 2 events, X and Y. Does X always happen before Y, or can Y sometimes happen before X? And what we did in a very simple case is look at the probabilities of those 2 options. If the probabilities are similar, then we made the assumption that there's no partial ordering between X and Y. On the other hand, if something can only happen once in a sequence of events, then once again, look at the probabilities that are occurring for that particular sequence. If it's very high that X always happens before Y, then you can, and it never happens with Y after it in the same sequence, then you could pretty much assure, I got that wrong, sorry. If there are 2 X's in a sequence, okay, is that legitimate or not? And so you look at the data, and if the data tells you that X only happens once, the vast majority of times, that's a possibility for a constraint to impose. Happens to be the case in some situations in baseball. So this is what we got. We were able, from streaming data, to represent the script. Now, don't try to read that. Well, maybe you young people can, but certainly not me. We were able to generate the script for a baseball game. Actually, a half inning of a baseball game, because we wanted to keep it simple once again. Once again, we took the first 500 half innings and generated the constraints. Then we ran the other 4,500 half innings through the algorithm, And this is what we got. Now, there are some imperfections I want to point out. When I was a literature student in college, I happened to take a course from a well-known writer. And he said that every good novel, the protagonist has a wart. This is our wart. Okay. It's true, too, by the way. There are situations where right now our algorithm is not sophisticated enough to recognize that two particular pathways should be collapsed. Now, I want to point out a couple things. Not only do we have the pathways, but we have the frequencies with which those pathways are taken. So those could easily be turned into probabilities, and once again, it's very useful for an analyst to know. Okay? So let me look at some very specific script instances. On the far left, the most common script you have for a half inning in baseball, based on the data we looked at, once again, it's focused on the data, is 3 straight outs, no runs. We also were able to pick up things like rainouts, so out 1, out 2, game over. We also were able to pick up, surprisingly, triple plays. And the reason that was surprising is because they're not that frequent. But I know, based on the way this algorithm is written, that it had to happen at least twice in that 4,500 half innings that we used to generate the script. So that's an unusual event, but it happened, right? On the far right, here's a rare half inning that does not appear in our script. Now, this half inning, I haven't looked back at the data, but I can give you an example. There's a fly out to the left fielder. He grabs the ball. There's man on first and third. The guy on first is off base. He's running to second. The guy flings the ball home to try to get the guy who tagged up on third going home. He doesn't get there. The catcher then throws the ball back to the second baseman who tags out the guy who's trying to go from first to second. So you have a run and 2 outs on the same play. The surprising thing to me was that in this set of data, it only occurred once, or something like that. There are other ways you can generate this same script. So it's kind of interesting. What did we learn? Well, you can induce scripts from streaming data, assuming you could identify the events. Remember, I talked about going to the baseball data because the event recognition capabilities are not terribly good, but we're going to be working on that in the future. Second, the constraints are necessary to avoid invalid pathways. We had to learn the rules of baseball in some sense, okay? And the better you are at learning those rules on the fly, obviously the better you're going to be at generating the script. And even this very simple test case was incredibly hard in some ways. We chose to simplify it by looking at baseball. Had we not done that, we would not have gotten nearly as far in terms of the script learning piece. We simplified the types of events. We didn't care if you scored 1 run, 2 runs, 5 runs, or 100 runs in an inning. We just said there were runs scored. And you'll see instances, if you looked at that big script, where it will say X runs scored. We didn't care. We only focused on capturing the events that were directly related to building the script. So there are lots of other things that go on a baseball game that we didn't capture, or information we didn't capture. For example, we didn't capture the name of the catcher who threw the ball to the second baseman who tagged out the guy coming from first. That was not important for the structure of the script. Finally, we took the simple path. We didn't have any cycles in this. I haven't even thought whether you can get that in a baseball game, but who knows? Based on those things, we learned a lot about this, and it's kind of an interesting thing to pursue in the future. So what are we doing for next year? First, we're going to focus more on event recognition and extraction. I already hinted at one of the things we're going to do. There is curated data out there, and in fact, the NASIC folks have some data we hope to get, where they have basically taken some data, declassified it in some way, or it's not classified data, so we can then use it, hopefully, some of the analyst reports to give us some more carefully curated data that we can then use to train our system to do a better job at learning scripts. The other thing we have to do is we have to be able, ultimately, to be able to recognize scripts across multiple documents. Once again, I said that's something where people really haven't touched that at all. It's a lot, there's a lot of progress that is needed there. There are people at Carnegie Mellon working on that problem, and we're going to be pulling some people in. We want to extend script learning, obviously, to more meaningful data. It's great to be able to build this for a baseball game. Can we build it for a real situation of something occurring in the real world? That's going to be a key. And finally, notice, well, in a baseball game, you really don't have any partial scripts. What happens if you have event A, event B, and event C, and that's the script? Okay? But suddenly you get data that has A and C. The fact that there's not a B in there does not mean that B didn't occur. It means that you were not able to identify it in the data. It may have happened. It may have been outside of your sight. It may have happened in a way that you don't quite understand. So you have to be able to recognize when partial scripts relate to more complete scripts. And actually, my own personal opinion is that it's going to take a lot of analyst feedback to be able to understand that. It's a hard thing to do. And that's it. Any questions?